Good evening, friends. My name is Vishwas, and today I'm going to discuss on the topic of computational SSDs for semantic image retrieval. Let's get started. So let's talk about the problem of semantic image retrieval. There are multiple approaches for image retrieval, and some of these deep learning techniques are either doing a tag-based retrieval or user queries, basically captions derived from an image, or user query, let's say scene graphs derived from an image. So there is scene graph based methods which will generate scene graphs out of images, and user can query these scene graphs, or there is tag based methods where some tags from deep learning objects are extracted and are stored. So the analytics derived from the image is stored in a database. Different methods use different types of database. For example, a tag-based search uses a key value DB, and a scene graph-based retrieval uses a graph DB. Scene graphs are usually the state of the art in terms of semantic image retrieval, because they're the first one who really captures the relational semantic mapping between the objects captured from deep learning models. So let's talk about the problems in semantic image retrieval that we discussed in the previous slide. So there's actually no standard format to store analytics from deep learning algorithm. Every algorithm requires a different kind of database to store the data. And maintaining a database on low compute device really adds to the complexity of design. So the lack of unified structural format to store the deep learning analytics is really the problem, and different deep learning techniques basically store and first extract and then later store the analytics in different formats, making it very difficult to really connect the user query pipeline to the deep learning pipeline for image retrieval. Let's talk about the constraints. When we have to design a semantic image retrieval model which is unified inside an SSD, we have to think about low memory footprint for the models, because most of the deep learning models consume a lot of memory. We have to think about a very high level of accuracy, because we can't really afford that the user query results into an image which is not really depicting the objects that the user is searching for. In short, it should not result into false positive. And we know that higher accuracy demands heavier models. So we have to think about this constraint. We have to have a very low latency for search as our last constraint. And we know that the RAM requirement grows exponentially as number of images in the database increase. So overall, the search time takes a hit, and we have to be very careful in balancing the low latency for search with the RAM requirement. Let's talk about the architecture on an SSD with a unified semantic image retrieval framework. Basically, it consists of two entities. One is the application, which is basically going to give the images as input and going to do the indexing of the images, and finally giving the user the option to enter the user query and give the images that are matching the user queries back to the user. So that's really the applications part. And on the SSD, we have two subsystems mainly. One is the NVMe subsystem, which is gonna have one NVMe vendor-specific I/O handler, which will fetch the NVMe vendor-specific commands coming from the application for this image upload and user queries, and it's going to redirect the image image and query parts to a separate quad-core ARM CPU. So that's the new thing that is going to do the machine learning part. The components on the quad-core ARM CPU are 4 main components. One is the image captioning part that we'll discuss later in detail. Is gonna have one more component called sentence-based transformer model called an SBERT model, which will generate an embedding out of the image captioning model. And then for faster search, we're going to have one more component called Annoy indexing, which is going to result into the faster search of the user queries inside these embeddings. And then this unified image retrieval framework is going to store and retrieve images from the SSD backend. This is how the architecture looks like inside the SSD for our framework. So let's talk about the solution in terms of a pipeline. We discussed an image captioning model, which is going to generate, let's say, triplets called subject, verb, object. And first, we are going to do a deduplication of these triplets using a scripting layer. So if you see in the figure below, there are 2 pipelines called 1 and 2. One is the image pipeline. Second is the query pipeline. So in the first image pipeline, once the image is uploaded, there is a functional local endpoint for a deep learning model, which will take the raw analytics from the deep learning model, and it will feed it to a scripting layer, which is going to deduplicate the triplets and basically pass it on to the embedding module, the SBERT, the sentence transformer model, which is going to generate the embedding vector of a 768 dimension encoding vector, which will be then feed to the indexing layer, which will generate the index tree using Annoy indexing. So that completes the image pipeline. And then we have pipeline 2, which is the user pipeline, which takes the user query and then feeds it to the same embedding module to generate an embedding vector. And this vector is going to be searched in the master embedding dictionary that was created and stored as part of indexes earlier. And then finally, the one match which is very close to the current user query would be returned. So this match would be top 5 or 10 images which have the least distance with the master embedding list. So this distance is computed using angular distance from the embedding module. This is how the 2 pipelines are generated and are connected. Let's talk about the CMS BERT sentence transformer model. This is really the main component, how we are connecting the deep learning model to the user query. So basically, if you see all these transformer models, usually they work using word tokens, and which will generate separate words for each tokens. But this sentence-based BERT model implements an additional pooling layer on top of these BERT models. So they generate like one single sentence instead of, let's say, a separate token for each word, right? So there are different polling strategies that are implemented by these SBERT models. And finally, what we get after the pooling layer is the embedding vector of a text that has 768 dimension. But the main thing is like there is just one text which is a sentence, and this is how we can basically compare two sentences out here. Let's say the movie is superb is one sentence, and the good movie is another sentence, and both will have a similarity computed using any of the distance formula, let's say a cosine distance or angular distance or a Manhattan distance. That's how we can compute the similarity of a particular sentence. So that's the main reason why Siamese BERT network is picked. It beautifully captures a semantic context of a particular sentence between basically capturing the relations between the words. Let's talk about the deep learning model for computer vision. It could be any model really. It could be one of the popular image captioning model, or something like a scene graph generation model. Essentially, we are going to capture the text which is basically depicting all the major objects inside an image. So here you see a picture of a lady playing tennis. So finally, it's going to result into some kind of a text which is something like a woman is playing tennis. Basically, if you see, this will result into one of the regular CNN models, which is then fed into a transformer model, which is attention based, and it's going to generate these the text which is basically trained on a rich corpus and generates a textual description of one particular sentence. So that's how we pick an image captioning model. In terms of design decisions for this uniform embedding model, there are four main decisions, which are basically the nature of embedding. We selected, like I said, the context-based embedding model over word-based embedding model because it captures the semantic intent, and it is having less RAM footprint. And then we have this embedding module that we selected was the Paraphrase Mini LM-L3 V2, the SBERT model. It consumes about 375 MB of RAM, and for a 3% drop in accuracy, we get about 50% more RAM. So we can actually get about 768 MB of RAM if we can if we really need 3% more accuracy. In terms of index, we use the Annoy indexings to store embeddings in a tree to reduce the storage of embeddings in RAM. We confine the number of trees to 100, and the finalized angular metric with number of trees was 25. Angular threshold, I talked about the angular threshold for being used as a distance criteria. We use a threshold of 1 to separate relevant queries from irrelevant queries. This is how we compute the distance between the embedding generated from user query and the embedding vector generated earlier from deep learning models. And we compute the distance from the top 50 entries to select the top 5 or 10 entries, which are really closest. That's how we do our design decisions for this unified framework. Let's take a deeper look at the indexing. So the indexing was created from about 1.2 million embeddings in one batch. So basically, we had 10 embeddings per image, so about a batch of 12K images, resulting into 1.2 million embeddings. And this index was later stored in the memory of this separate quad-core ARM and used for search. And for each of these deep learning models, the index creating was created using Annoy. And 5 distance matrix, Angular, Euclidean, Dot, Hamming, and Manhattan. These were used with trees varying from 10 to 100 to arrive at the final configuration. And all of this was evaluated for optimal number of trees. To search on embedded systems, like I said, in one batch, we had an index created for 1.2 million embeddings that took about 770 MB of RAM. And when loaded in RAM using the indexing, we only required about 1 MB of RAM. Index creation and search time was computed, and in one batch, we were able to create 1.2 million embeddings, right? And and in one batch, we could create about 100 trees. Let's take an application view. If you see the images here on the application, we have to click on Add to Advanced Search. So this option will add all these images to the deep learning pipeline and feed it to the deep learning model, get the triplets generated out of it. The scripting layer will deduplicate them, and then the embedding module will generate a master embedding list, and a dictionary is created, which would be stored using an Annoy indexing. And this is the user query part. Let's say there is a query called snow on mountains. So this query would be again converted using the same embedding module to a vector, and then search in the master embedding dictionary list created earlier. And it's going to generate, let's say, these 3 matches that are found. And if you see, all these 3 images have snow and mountains, both the objects, and there is a relation that snow is all on mountains. So it results into more than 97 to 98% accuracy, this particular query. And in general, our model achieves more than 97% accuracy with this technique. So that's a view about the deep learning model and the user query, how they are connected inside the application we saw. So in summary, friends, we defined a uniform framework for semantic image retrieval, which basically connects various deep learning models for a particular user query to do semantic image retrieval. We defined a separate quad-core ARM CPU inside the SSD to do the image captioning, embedding, and searching part. The Annoy indexing was used for fast search on the SSD inside the quad-core CPU, so which results into a less footprint for storing the embedding and a faster search. That's all I have, friends. Please take a moment to give feedback. Have a nice day. Thank you. Bye-bye.